Hello class and welcome back. This week we will be going over vat polymerization additive manufacturing. This includes several different types of 3D printing, most notably SLA and DLP. In this video quiz we will be going over information and I'll be asking you some questions along the way. You'll be able to go back and watch this as many times as you like, and I'll be uploading the slideshow as well. So first things first, what is vat polymerization? Vat polymerization is a process where you use a container, or vat, filled with a photopolymer resin. Then you project light into the photopolymer, causing it to harden. This can be done layer by layer until you have a solid object. It's like FDM, but with lasers and goo. You might be saying, how have I never heard of this type of 3D printing before? Vat polymerization sounds complicated. Well, the shorter answer is, you have heard of it, just by a different name. Vat polymerization is a broad class with multiple types of 3D printing encompassed in it. This includes SLA 3D printing, like the Formlabs printers use, and DLP, or digital light processing. This is used by a lot of companies like Anycubic and even Prusa. So now what is a photopolymer? It's a material that reacts to radiation by ultraviolet or UV wavelengths of light, but also some visible light. When a photopolymer, which typically just looks like a slime or goo, has light shined or irradiated onto it, it undergoes a chemical reaction and solidifies. The process is called photopolymerization. It's typically a pretty complex process and uses many different chemicals. We won't be going super in depth to the chemistry of what's happening, but you do need to know the basic process. We'll go a little bit deeper with this in a few slides. Photopolymers were actually developed in the 1960s for the coating and printing industries. When I say coatings, I mean things like glossy paper, photoresist on computer PCBs, and things like that. It also is used pretty heavily in the dental industry. If you have ever had a cavity filled and the dentist put a blue light gun with an orange shield in your mouth, you've got a photopolymer right there with you as we speak. Now the paper industry is a pretty far cry from 3D printing, but in the mid-80s, a gentleman by the name of Charles Hull was experimenting with UV curing materials and lasers. He was running a scanning laser over a photopolymer and discovered he could produce patterns by scanning one layer over the previous layer. This was done over and over and created a solid 3D part, and boom, vat polymerization additive manufacturing was born. That term, vat polymerization, was coined to encompass stereolithography and other related processes. There are many types of light that can be used for vat polymerization. It depends on the material being used, but the sources can include ultraviolet or UV, as we've already talked about. UV is the most commonly used light source in vat polymerization. You can also use visible light, gamma rays, X-rays, and even electron beams. These can all be used for their own applications, and believe it or not, different types of light can make different levels of accuracy in the print. So how does all this work? Shine a light on some goo and it turns into a solid, right? Well, yes, but there's a little bit more to it than that. Vat polymerization polymers are made of a few different materials. These include photoinitiators, reactive dilutants, flexibilizers, stabilizers, and liquid monomers. Don't worry, you don't really need to know all these, but I do want you to understand a bit of what's happening in the process. Let's use UV light for example. When a photopolymer, which remember is still liquid at this point, is exposed to UV light, the photoinitiator inside of the photopolymer undergo a chemical reaction. In this reaction, they interact and react with the monomers in the photopolymer and start to form chains. These chains are called polymers. Polymers are really strong as far as molecular bonds go. They have covalent bonds, which means atoms in the polymers are actually bonded into a molecule. A real-life example of a covalent bond is water, or H2O. A water molecule is made up of 2 hydrogen atoms and 1 oxygen atom. But in a practical sense, we don't ever see water in the real world break down into hydrogen and oxygen. We see water change from a solid to a liquid to a gas, but it doesn't usually break from the H2O molecule. This is the same type of bond these polymers are making, which means that parts are bonded together really well. This doesn't mean that the parts are super strong though. Many resins are extremely brittle and would shatter if dropped on the ground. Though FDM parts, like we print on the Dremel machines, are just physically bonded in their layers, they typically have more physically sound build than a vat polymerization print. This just means that if I wanted to make something like a replacement foot for a keyboard, it would typically be better to use an FDM machine rather than vat polymerization processes. There are always new photopolymers being invented though, so one day this may not be the case at all. There are 3 different types of vat polymerization, so let's take a look at them. The first type is vector scan or point-wise vat polymerization. This is when you use a laser and a scanning mirror to harden the resin in a precise place. One of the better known companies that make printers using this type of technology is Formlabs. Let's watch a quick video where they describe the process.
All 3D printing technologies create solid parts from 3D models layer by layer. Among them is SLA. SLA stands for stereolithography, a 3D printing process that uses a UV laser to cure liquid resin into hardened plastic. Upside down or inverted stereolithography is the most common SLA system. Depending on the machine, resin is either poured into a tank by a user or dispensed automatically from a cartridge. At the beginning of the print, a build platform is lowered into the resin, leaving only a thin layer of liquid in between the platform and the bottom of the tank. Galvanometers direct the UV laser through a transparent window at the bottom of the resin tank, drawing a cross-section of the 3D model and selectively hardening the material. The print is built in consecutive layers, each less than 100 microns thick. When a layer is complete, the part is peeled from the bottom of the tank, letting fresh resin flow beneath, and the platform is lowered once again. Originally developed in the 80s, SLA was confined to large industrial machines until recently. Today, desktop stereolithography offers affordable, high-resolution 3D printing that fits conveniently in your workspace. SLA allows for the use of a wide range of materials with diverse physical properties. Whether you're an engineer, product designer, sculptor, jeweler, or dentist, there's a material for your application.
The next type that we're going to talk about is mask projection or layer-wise vat polymerization. With this type, rather than using a laser to harden a tiny bit of resin at a time, you actually harden an entire layer of resin at once. There are lots of ways to do this. One way is to use an LCD screen to block out light except for specific areas, then use a DLP projector as a hardening source from underneath. Another way is to use an LCD screen like a cell phone screen to harden the resin, once again from underneath. One company that uses this technology is Prusa. Let's watch a video on their new SL1 printer and how it uses mask projection. The last type is the 2-photon approach. There isn't a ton of info out there on these due to the expense of the equipment and the limited consumer use at the moment. The 2-photon approach literally prints with atoms. In the video we're about to watch, they print a castle on a tip of a pencil lead. This isn't very practical, but it does have really good implications for the future. Be sure to watch the clock on the right hand side of the screen. This is super speed on the playback.
The following video shows 3D printing of a castle via multi-photon polymerization technique. Ultra-short pulse laser-based 3D printing. The laser scans through the volume of photosensitive material. Locally induced photopolymerization solidifies material in accordance with a 3D model. Once a layer is finished, the laser focal plane moves to the next layer. The true 3D capability of the method eliminates the need to deposit material layer by layer. Due to non-linear absorption, spatial resolution in the submicron range can be achieved. Scanning electron microscope image of a castle printed onto the tip of a pencil. Thank you for your attention. For more information, visit our website.
So based on all these things we've talked about, you've got some assignments to do. The first is a discussion. This involves you making and commenting on two other classmates' posts, so go ahead and get that done early. You will have an assignment and a quiz also. Good luck, and if you have any questions, feel free to reach out to me and have a great week.